So this is the last lecture that I'm going to give about randomized algorithms for their own sake. The stuff that I'm talking about in the lecture today will not show up on any exam, will not show up on any homework. I'm just showing it to you because I think it's cool and because I think if you're dealing especially with large amounts of high-dimensional data, it's a useful tool to have in your algorithmic toolbox. On top of that, I'm going to have to apologize that the lecture is likely to be fairly sketchy. I'm not going to go through the analysis of the algorithm in explicit detail, but I'm going to try to give you at least a flavor of how the algorithm works. And then if you find yourself in a situation where you need to compute nearest neighbors, this is at least one way that you can do it, and you can find the details in, among other places, Wikipedia, which has links to actual implementations of this stuff. We are, I think, relatively close to having the midterms graded. I think there's a fair chance that we'll have them done by Thursday, but end of the week, I think is a near certainty at this point. And as soon as those are back in your hands, I'm happy to answer whatever questions you have about them. There is one final randomized analysis homework up on the website. 2 more questions due a week from today. Both of those questions about streaming algorithms. Again, both relatively simple modulo doing the analysis. Are there any administrative questions? Okay. So, as I said, this lecture is more or less just for fun, for some personal and rather perverse definition of fun. Feel free to stop me and ask questions if anything comes up. But as I said, this is not stuff that you're going to be responsible for in any homework or any exam. So, nearest neighbor searching. So this is really a data structure problem. We've seen other kinds of data structure problems that are solved by binary search trees, that are solved by hash tables. You've seen priority queues and so forth. What the nearest neighbor searching problem is, I'm given a set of points. Let's call this set P, P1 through Pn. And I want to build a data structure so that later, given another point Q, we can quickly find the minimum over all points P in the data set that we preprocessed, the distance between P and, the distance between P and Q. All right, so I'm going to assume that there's some distance function that is sort of intrinsic in the problem. If these are points in the plane, for example, it's natural just to compute the Euclidean distance, the square root of the square of the difference in y coordinates plus the square of the difference in x coordinates. In other contexts, this distance Euclidean distance might not be the right thing. But generally, I'll assume that this is some well-behaved function that obeys the triangle inequality and it's symmetric and it's 0 when P and Q are exactly the same point and positive otherwise. So it's a metric. So if I imagine, Euclidean distance, as a sort of standard, there's a standard example of a distance that I might want to do preprocessing for and do nearest neighbors for. I've got points flying around in some d-dimensional space. Depending on what you're doing, these might actually be physical dimensions. So for example, the canonical example is where is the nearest Starbucks? So the data set is all Starbucks on the planet, or at least in some square region of Google Maps. And the query point is where I am, and I ask Google Maps, where do I get my Frappuccino? Here d is equal to 2. It might be, here is, my spaceship is lost somewhere in space. Where is the nearest habitable planet? So I pre-process all quintillion habitable planets in the universe into my data set. And then I want the one that's closest in Euclidean distance. And when I'm dealing with Euclidean distance, this problem is reasonably well understood. And in this case, there are fast algorithms with small data structures. When d is small. Okay. Unfortunately, not when d is big. The larger this dimension of the data gets, the more difficult it is to solve this problem quickly. Now, there's always this sort of brute force algorithm, which just says, in a for loop, compare q to every point in the data set. Right? Compute the distance. I assume that Euclidean distance can be computed in time proportional to the dimension, and I have endpoints to look at. So the brute force is linear time in the number of numbers I have to write down to represent the data, which means I have no data structure at all. Right? Normally, we like to build some pointers and some comparisons and some pre-computation into the data structure so that when we do these queries, we can save some time later. You already know how to solve the problem d equals 1. Okay, so I give you a bunch of points on the line. All right, just here's a one-dimensional Euclidean space, and there are some points on the line that you want to be able to pre-process so that later when I ask about some point q, you can quickly tell me that its nearest neighbor is this point p immediately to its left in this case. So how do you solve this problem? Binary search, right. So all I have to do is store the points in a sorted array. I do a binary search, and that finds the point immediately to the left and the point immediately to the right, and one of those two is guaranteed to be my nearest neighbor. Great. So this uses, logarithmic space. Logarithmic query time using a data structure that takes linear space. Right? This is sort of the ideal case that we would, the best we could possibly hope for, because it's essentially equivalent to doing ordered dictionary things, just finding the predecessor, finding the successor. Once you find the nearest neighbor in constant time, you can find the predecessor and successor because you know that if your nearest neighbor is a little bit less than to the left of p, its successor is going to be the next one. Okay, so this is more or less the same as the binary search tree problem. Turns out that there is a data structure with exactly the same space and time bounds for the case d equals 2, which uses a structure which I won't be able to tell you too much about given the time and the background that we already have, but it's something called the Voronoi diagram, named after somebody who discovered it in 1906. But of course, he wasn't the first, don't worry. There's a picture of a Voronoi diagram in one of Descartes' books from 1650 something. Okay, so this is a Voronoi diagram. The red points are the data set. And what I've done here is I've split up the plane into regions called Voronoi regions with the property that if a point lies inside one of these regions, its nearest neighbor is the point, the site in the data set that corresponds to that region. So every one of these regions contains exactly one of the data points. And I've drawn the lines, not exactly, of course, but the mathematical definition is I split the plane up into regions that are defined by saying all the points in the plane whose nearest neighbor is this point. Okay? I could do exactly the same thing for the one-dimensional case. And for the one-dimensional case, a Voronoi diagram just consists of the midpoints between all the points in my data set, which is easy to compute once I've sorted the points. I just average every adjacent pair. And then I could do my binary search over those midpoints instead of over the original data points. Okay. So as long as I can figure out which one of these intervals my query point lies in, my nearest neighbor is the corresponding, the only data point inside that interval. And the same is true in 2 dimensions. And in fact, the definition of Voronoi diagram extends without modification to any metric space at all. Okay. The problem is that, well, the nice thing is that when you're dealing with a Voronoi diagram in the plane, it's a planar graph. Planar graphs have this wonderful property that the number of vertices minus the number of edges plus the number of faces is 2, where I count, when I'm counting the number of vertices, the vertices here are these so-called Voronoi vertices, the points where the three or more Voronoi regions intersect. The vertices here include one vertex off at infinity. And in this case, the number of faces is exactly one face, one region for each of my data points. So one of the consequences of this is that the number of vertices is at most 2n minus 4. The number of edges is at most 3n minus 6. Number of faces is, of course, just n, the original number of points. And so this whole structure can be stored in a data structure of linear size. I list these points and their vertices and their coordinates. For each pair of points that's connected by a Voronoi edge, I say these are the edges, and the faces are more or less described implicitly by the coordinate structure. Okay, so I can just store this in a graph, and it only has linear size. When you go to higher dimensions, the complexity of this thing gets bigger. So in 3 dimensions, you don't just have vertices, edges, and planar regions. You've got 3-dimensional blobs that are your real Voronoi regions. And the complexity goes up to something like n squared in the worst case. As you go higher and higher and higher dimensions, the worst case complexity of these things grows exponentially with the dimension. So you don't want to build one of these things I mean, and I say in worst case, I say, well, in practice it's a bit better than that. In practice, it's not 2 to the dimension, or sorry, in the worst case, it's about n to the dimension. In practice, it's only about 2 to the dimension times the number of points. But still, once the dimension is about 10, you really want to stay as far away from these things as you can. It's just going to blow up. Okay. Now, in the 2-dimensional case, you've got 2 problems here. One is you have to build this thing. And 2 is you have to figure out when you give me a new query point, which region it belongs to. And it's not obvious how to do either of these things. At least it certainly wasn't obvious the first time I saw how to do this. And so let me give you not a complete analysis, but again, just some intuition about how this works. The way I'm going to build this structure is I'm going to pick one of the points at random, build the structure for everything else recursively, and then add that one last point. Okay, so let's suppose that now I want to build, let's make it green. I want to add this point to my Voronoi diagram. Okay. For now, I'm not going to tell you how this works, but somehow magically it's possible to find out which region this new point lies in. And once you know which region this new point lies in, you can sort of see that the boundary between these 2 points is all points in this region that are closer to the green point versus all points that are closer to the red point. This is a straight line, and in fact, it's the perpendicular bisector of those 2 points. Okay, so I can build that perpendicular bisector quickly, and then I sort of wander into the cell that's just to the right there, and then I trace out the new perpendicular bisector between the green point and this red point over here, and that takes me to the next cell. And I can trace out that perpendicular bisector, and that takes me to the next cell, and eventually this all closes up. That is the Voronoi region of the green point, and after walking around in that circle, I can do a bit of data structure manipulation to throw away the stuff inside that green polygon, and there's my new Voronoi diagram. Now it looks like this might be complicated, but remember I said I'm going to choose a random point to be last. And remember that the total number of edges in the whole diagram is only linear in n. So if I choose a random point to be last, the expected number of edges that I'm going to insert is only 6. Which means the total expected work that I do walking around this polygon is only a constant. And therefore, by linearity of expectation, the total amount of work I do modifying the whole Voronoi diagram over the entire random sequence of insertions is only linear. By the way, I just almost explained randomized quicksort. There's only one spot. I mean, this is the idea behind this is actually very similar to the analysis of randomized quicksort if you look at it the right way. The one part that I've left out is I haven't told you how to figure out which region that green point lies in. And the way that I'm going to do that is, in fact, the data structure isn't going to forget the stuff inside that last green cell. Okay? So if I want to do a query, say for this point x, the way that I will do it is I will say, okay, I already have the data structure for the first n-1 points, and figure out which region I'm in for those n-1. And then when this new point comes in, I can say, oh, did that new point, I've sort of flagged this region as something where the new point actually touched the region. And then I say, oh, well, in constant time, I just have to decide whether this point is on the green side or the original red side of this line segment. Constant time. If my query point is over here, then inserting the last point had no effect at all. And so my data structure can actually just immediately return the right answer. And if my query point happens to be inside the green region, it'll notice because it's inside one of the black Voronoi regions that was modified by the green point. And again, in constant time, I can figure out it's actually inside the green cell. Now, again, because of the low degree, the small number of edges, the probability that the last point changes the answer, the last point actually creates some work for my query point, is only about 6 over n. And when I have to do the work, I only have to do a constant amount of work. So the expected amount of work that I have to do to answer the query that's caused by that last point is order 1 over n. So I do expected 1 over n work for the last point. I do expected 1 over n minus 1 work for the second to last point. I do expected 1 over n minus 2 work for the third to last point. And in general, counting forward, I do on average about constant times 1 over k work for the kth point that I insert. So the total expected amount of work that I do is some constant times the harmonic number. Okay. So again, I've sort of deliberately not written anything down because I want the intuition to go into your head. But each insertion requires order 1 expected modification. And each query requires 1 over n expected work for the nth point, which means order log n expected work altogether, expected time altogether. Okay. So you can actually phrase the construction of trees or randomized quicksort in exactly the same way. Build a, recursively sort n minus 1 things, leaving out that one that you omitted, and then trace the history of that one last thing. And it turns out that you get exactly the same n log n bound that you get from the analysis that we already did in class. Okay. There are other ways to do this that don't require randomization. You can actually build this Voronoi diagram in n log n time, worst case, no high probability. You can actually do the nearest neighbor query in log n time, no expected, no high probability. It's completely deterministic. But the algorithms, the intuition behind the algorithms is considerably more complicated. Yeah?
I think I missed the point here. Where did you get the constant 6?
Okay, so every edge has 2 sides.
Okay.
There are about 3 n edges, and there are n regions. So the average region has 6 sides. On average, right? So if I pick a point out of the data set at random and ask how many sides does this Voronoi region have, the expected answer is 6. Actually, slightly less. And that's just, that's just an artifact of the number of edges being small. Yeah.
How you actually know that your point lands at a specific region? I mean, you already calculated that before, but actually, how do you calculate that?
So the way I figure out where that green point lands is I do a query in the data structure I built for the first n minus 1 points.
X marks here.
Yeah,
How do you know that it's in that region?
because that's what the data structure tells me. That's what I'm asking the data structure, which region is this point in?
So that is not discussed here. I mean,
No, that's exactly what I just discussed, except that most of it was done by the recursion fairy. I built a data structure for the first n minus 1 points, which the recursion fairy makes work.
Yeah.
Or, said differently, which, by the induction hypothesis, tells me which region this x lies in. Now I just have to tell you how to tweak it for adding this last point to the data set.
Giving you the x, the point x and y, the coordinate of the point, then how you know that it's in this region?
The recursion fairy told me which region it's in. What's the base case?
What's the base case? Yeah.
1 point. Which region is it in? That one. How do I tell when I add the second point which region it's in? Well, it's either on this side of the line or that side of the line.
Okay.
3 points. It's either on this side of the line or that side of the line.
So actually do the comparison there.
Yeah, so I have to do a comparison. For example, for this first x that I drew, the last point that I inserted said it actually changed the shape of this region. It cut off that corner.
Yeah.
And so the data structure is going to notice that and say, oh, but for the last point, you really have to check whether this x is above or below this line. The checking of whether a point is above or below a line can be done in constant time. It's just a coordinate comparison.
So, are you sort of building the data structure on demand?
Yes.
Query?
No. So when I'm the way that I build the data structure is I insert the points one at a time. It's like the way I would build a binary search tree. So I insert the points one at a time. And I use the pattern, the data structure that I've already built for the previous n minus 1 things when I do the insertion of the nth thing in a binary tree.
Yeah.
And that insertion algorithm for a binary tree looks exactly like the query algorithm for in a binary tree. The query tells me where to put the next item when I'm building a binary search tree.
So you just try to insert it, but you don't actually.
So the way that I build the data structure is one at a time. I follow the query algorithm for the part of the data structure I've already built, and then I do a little bit more work.
And how is it possible to be less than the 01?
So these are the details I haven't told you. Okay. So when you wander through the data structure, you end up in a particular record, right? And when I inserted that green point, I modified some records and added new outward going pointers from those records to other parts of the data structure. But when I queried this purple point, I didn't end up in any of the data structure records that were touched by the green stuff. I just ended up with a record that's labeled return. So the data structure is this complicated DAG that you trace through. And when I inserted the green point, I added some new nodes. When I do a query, I might end up in a different sink that isn't touched by the green stuff. Right, I'm deliberately being vague because the details require a bit of effort to actually walk through. Yeah?
What if you have multiple insertions?
You do them one at a time in random order.
Well, if you have any insertions that change the shape of the same region, then we'll have.
Okay, so the analysis here is crucially relies on the fact that I know all of the points in advance, and I'm inserting that set of points one at a time in random order. So the first step is run the Fisher-Yates shuffle to randomize the order. If I wanted to insert an arbitrary point, things get much more difficult because that new point might have a very complicated region. I haven't chosen the point randomly, I've chosen it adversarially. And then the analysis just breaks down because there's no averaging anymore. Yeah?
When you're searching for a point, you should be reducing at each level. So your expected goal is still ordered 1 by n plus 1.
No, it's really just 1 by n.
But
The idea is that the record in the data structure has probability when I insert the kth point, the record in the data structure where this point would land changes with probability 1 over k. Meaning there's an outward pointer that says do a comparison only with probability 1 over k. Right? Most of the time, for most of these cells, when I insert this green thing, the record in the data structure corresponding to this cell doesn't gain any new outward pointers. So when I walk through the data structure DAG, I just hit the end and I'm done. It's like in a binary search tree, when I insert something small, a query to something big doesn't change.
So you're not really recursing.
No, I really am recursing.
What is this data structure looks like?
It looks like a big giant DAG. It looks like an ungodly mess. Okay, but
DAG is like a vertex is a green point. Is a blue point.
the vertices of the DAG correspond to regions,
Or regions.
but when the region changes shape,
You know, break it to.
that becomes a new node.
Okay.
Okay, so there's a region for this black. There's a node in the DAG for this black polygon, and there's also a node in the DAG for this black polygon with this green corner cut off.
Then how could you represent a region? Inside a node?
I don't have to, right? So this is the interesting thing about this data structure. Nowhere in the data structure, in the query data structure, do I ever actually have to explicitly describe this graph. I just have to describe what questions do I answer in order to figure out what region I'm in. And every single one of those questions is, am I closer to this point or to that point? Just am I above or below this line that's the bisector of these 2 points? So a lot of these questions are, you haven't given us enough detail to write the code. And you're right, I haven't. That was intentional. Let me answer one more query question here, and I think there might be one more question over there, and then I want to move on.
Just a quick question. Would it be possible for you to draw 3 points and a query X and just show us the walkthrough of
Sure.
the drawing
Okay,
to see where the query
so I'm going to start with, here's the query X. Base case, nothing. Well, I don't have a nearest neighbor. Okay. So now I'm going to insert my first point. That's my nearest neighbor. Great. Now I'm going to insert my second point, and when I insert my second point, the only region now gets split into 2. And because that region changed, the region containing this point changed, this point now knows it has to do a comparison against this line. It finds out that it's on the left, and we're done. Now I'm going to insert another point, say over here. All right. Now by inserting this point, I've modified both of these regions. Because the region containing X changed, X now knows it has to do a comparison against this line. Having done that comparison, it realizes it's on its left, it's still in the region corresponding to the point down here in the lower left. Right. Now, if I insert yet another point way over here to the right, that will change only the regions over here on the right. Now, because the region containing X did not change, X does not have to do any work. It doesn't even notice that I inserted this point. This is like I did a binary search in a binary tree, and I'm way over on the left, and then somebody comes along and inserts a point that goes way over to the right. Right? I do the insertion over on the right, but the point on the left doesn't care.
So the thing is that the queries exist before you insert any point.
Sort of. The trick is when I'm building the data structure, I remember how the data structure was built. And when I want to answer a query later, I walk through the history of the data structure.
I see.
a little, yeah, okay. Any other questions about Voronoi diagrams? Okay. So when things get into higher dimensions, as you might imagine, I mean, exactly the same idea still works. What breaks down is the analysis. You no longer have this planar graph property. Things can get quite a bit more complicated. There are some tricks you can play to bring down the query time at the expense of some space, but they're really ugly and complicated and not practical. What people actually do then in practice when they're faced with, for example, let me Google for pictures of Voronoi diagrams. And what Google's actually doing, if I upload a picture of a Voronoi diagram and say, find me similar pictures, is it's doing a kind of nearest neighbor query. It's saying, find me the picture in the Google database that is most similar to this, and then the next most similar, and then the next most similar, and so on. Right? But you'll notice if you just play around with Google image search for a little while, the order that you would probably manually sort the pictures is not exactly the same as the order that Google's given them to you. And the reason for that is Google isn't really answering the nearest neighbor query. Google's answering an approximate nearest neighbor query. Okay, so the input is the same. I have a cloud of points that I want to pre-process into some data structure. Later I'm going to have a query point. So again, if I imagine that I've got some cloud of points, and later I'm going to come in with a query point. Now, if I were solving the nearest neighbor problem exactly, I would get, I don't know, this point, which lies, there's some nice little circle there that it doesn't have any other points in it. Approximate nearest neighbor query, it's okay to return any point that is approximately nearest, right? So what I want is to return any point P in my data set such that the distance from P to Q is at most C times the minimum, let me call this piece of I, the minimum distance over all P in the data set. Okay, so this is the actual minimum distance. This is C times the actual minimum distance. And any point inside that larger circle is fine. Now, sometimes you can take this approximation factor C, and in some contexts you want this to be really close to 1. I want a point that is within 1% of being the closest neighbor. It turns out that because of the way geometry works in really high dimensional spaces, it actually is not that important to get within 1%. There's a kind of weird behavior where as soon as you're even kind of close, suddenly the number of points available to you, explodes. And so one of the side effects of that is it's really okay in some practical situations just to say, okay, fine, C is equal to 2. And even a point that is only at most twice as far away as your true nearest neighbor is useful. This is kind of what the Google image search is doing, where here the points are the images in Google's data set, or rather some feature vectors associated with those images. And your query point is the image that you upload, or rather some corresponding feature vector that Google computes quickly. Okay. And generally speaking, The smaller c is the slower your algorithm is going to run. The larger c is the faster your algorithm is going to run. Okay. The algorithm I'm going to talk about next actually plays this game a little bit even more loosely, which is I'm going to return a nice point with some confidence probability. Right, so I'm going to be in the realm of randomized algorithms that allow for some small probability of error. And again, Google is doing this. Occasionally, when you upload a Voronoi diagram and ask it for similar pictures, you will get a picture that has nothing to do with the Voronoi diagram. And it's just because, well, I'm sorry, delta is only set to 0.01. 1 out of every 100 pictures that Google gives you is just nonsense. Okay. And the way the basic structure that is underlies this algorithm is called locality sensitive hashing. So it's a variant of hashing. I'm going to compute a particular type of hash table for the points in my data set. And then I'm going to compute the hash value for my query point, and that will retrieve some points out of the hash table. And then I'm going to run through the points that I retrieve from the hash table, and by brute force, I'm going to calculate distances and return whichever one is closest. Or if I don't find anything that's close, I'll just return the one that's closest. It's essentially the idea. Okay. It turns out, though, to be a little bit easier if I take a step back. This is an optimization problem. I want to find, most of the time, approximately my nearest point. As with a lot of optimization problems, it's often useful to think about the decision version of this problem, where instead of saying, I want the nearest point, I say, I think the distance to the nearest point is about 150. Let me find a point that's within 150. Oh, I found one. Okay, now I think the nearest neighbor is within 75. Let me try to find something within 75. Oh, didn't find anything. Okay, it's between 75 and 150. Now let me do. So you can imagine doing a kind of binary search over the spectrum of distances, and provided that you can answer the question, is there a point reasonably close to me? You could use that to build a nearest neighbor search. Okay. So the actual problem is called the approximate near neighbor search. Okay, so again, I'm given a set P to preprocess. And then later, I'm given a point Q, and I'm given distances little r and big R. Okay. And the idea is if there is a point whose distance from Q is small, return a point P prime in P such that the distance is within the larger region. Okay. So if I were trying to solve an approximate nearest neighbor query, what I would do is I would say, okay, I'm going to guess what the minimum distance is. And I'm going to search over the space of possible guesses, essentially by doing a binary search. I'm going to guess that my nearest neighbor is within 1,000, so I'm going to pass in as my distances, little r is going to be 1,000, and capital R is going to be c times 1,000. Okay? If, in fact, my nearest neighbor is within 1,000, then there is actually a point that is within the smaller distance, little r. It will succeed by returning some point that is within c times 1,000, the larger distance. Conversely, if the data structure never returns any points, it just says no, then I know that my guess for my nearest neighbor distance is too small. I should make it bigger. If I actually get a result out of the near neighbor search, then that tells me that my estimate for my nearest neighbor is maybe a little too big and I should try to make it small. Okay. Again, I'm going to allow some small probability of error. Okay. And so now, modulo this sort of binary search, what I really now need to answer is this approximate nearest neighbor question. Now there is a technical difficulty here, which is that if I am actually dealing with points over some Euclidean space, the range of possible distances is actually infinite. And so the range of things where I need to do a binary search isn't fixed in advance. It's not a function of the number of points that I want to pre-process. And I'm going to end up actually needing to build a different near neighbor search data structure for every value of little r. So if I really did this binary search idea, in the worst case, I have absolutely no bound on the running time because I don't have a fixed range of distances to binary search over. That particular difficulty can be worked around. So the reduction from one of these to the other was probably the simplest one was worked out by Sariel about 15 years ago, back when he was a brand new assistant professor at the University of Illinois. It's cute, but given the time, I'm not going to talk about it. Okay. It's been implemented. You can actually look it up on the code that you can find on link from Wikipedia, but I'm not going to talk about it. In practice, for in a lot of situations, a binary search really is enough. All right. So this is the problem that we want to try to solve. If there's a point really close, give me a point that's kind of close. Okay. If there aren't any points that are really close, don't give me anything. Okay. Now, what is locality sensitive hashing? Basically, the idea is that I want a hash function that has the following property. If a point is really close to you, you and that point should most of the time hash to the same place. If a point is really far away from you, then you and that point most of the time should hash to different places. So I want the hash function not to do random collisions anymore. This is sort of the opposite idea from a standard hash function. I don't want the probability of a collision to be random, but rather I want the probability of a collision to depend on the distance between the points. Close points should collide more often. Far away points should collide less often. Right? And the way this would normally be phrased is something like this. If the distance between P and Q is less than R, then the probability that H of P equals H of Q is big. It's at least some probability I'll write as a capital pi. And on the other hand, if the distance between P and Q is large, then the probability of a collision should be small, little pi. Okay? If a family of hash functions satisfies this property, where the probability is, again, as usual, I select H out of that family, then this family is called a locality-sensitive hashing function family. Right? This family of hash functions is locality-sensitive. So let me write that down. All right, a family H of hash functions is locality sensitive if, and these parameters, the two distances and the two probabilities, these are telling you how sensitive, in what way is it sensitive. So if I actually go to the paper that defines this, it would say a family H of hash functions is little r, big pi, little pi, locality sensitive. But fine. I need I'm basically usually given the distances little r and big R, and I need to find a family of hash functions and compute the appropriate probabilities, capital pi and little pi. Okay, so I'm going to give you an example of a family of locality-sensitive hash functions. It is a ridiculously simple family, and it gives absolutely horrible bounds for these two probabilities, but it's enough to get off the ground and actually do more interesting things. So in order to do this, I need to consider, Euclidean distances are nice and they're beautiful, and this whole theory works for them, but it's a lot more complicated than just doing something a little bit simpler. So let me say now that my points are d-bit vectors. Okay, vectors of zeros and ones, and d is now is just the dimension of that vector. Okay, so I want you to think of these vectors as, for example, there's a 1 in the first bit position if the word the appears in that web page. And there's a 1 in the second position if the word of appears in that web page. And there's a 1 in the third position if the word an appears in that web page. And there's a 1 in the 48,000th position bit if the word spaghetti appears on that web page. Okay, so you just have a vector that tells you which words appear on which web pages. Okay. But now let me define the distance between 2 points as the number of ones in their symmetric difference. So this is the number of words that appear on one web page but not the other. This is called the Hamming distance. This is the number of bit positions that are different in P and Q. Right? So if P is 0, 0, 0, 0, 1, 1, 1, 0, 1, and Q is 0, 0, 1, 0, 0, 1, 0, 0, then I've got 1, 2, 3 positions where they differ, so the distance is 3. Okay? This is the metric that I want to think about now. And it turns out, again, by work that Sariel did together with a couple of people from Stanford, that this is, in some sense, the only interesting case. once you can solve the Hamming distance problem, you can, by a series of reductions, build up to a data structure for other kinds of metrics. All right. So let me define a function. I'll call this h sub I of p. This is the ith bit. Okay. And now I'll define capital H to be all such functions. So my hash function is basically 0 or 1. Does this web page have the word spaghetti in it? Or does this web page have the word quiz in it? Or does this web page have the word web in it? Or does this web page have the word in it? And so what I'm going to do is pick a random function out of this family and ask what's the probability that I'm going to get a collision. Well, picking a random function out of this family is the same as just picking a random bit position, and the collision just means the two bits are different, are the same. Sorry, the two bits are the same. Because there are only two buckets, 0 and 1. So what is the probability for this particular pair of bit strings? What is the probability that h of p is equal to h of q? There are 9. Right. So this is, well, actually not 3 over 9, because you get a collision if the bits are the same. Okay. In this particular case, there are 3 bit positions that differ, and there are 6 bit positions that don't. So the probability of a collision is 6 over 9. 2/3 of the time, these two strings will collide. In general, the probability is going to be d minus the distance between p and q over d. Or I'm going to write that as 1 minus the distance from between p and q over the dimension of the vectors. Yeah?
So does the hash function return a single bit?
Yes. I'm hashing into a table that has 2 spots, 0 and 1.
Is that deterministic then?
No, because which bit, this index I, I'm choosing uniformly at random. I've got a family of all these d hash functions. When I'm doing this probability, that's all, as always when I'm talking about hashing, the probability over my choice of hash function, which I choose randomly from this set. Okay. So it's a very different way of thinking about hashing. Again, I'm not trying to distribute things in a hash table to prevent collisions or minimize collisions. I actually like collisions. But I only like collisions if the distance is small. And so you'll notice here that this set of hash functions actually satisfies the definitions at the top of the page. If the distance between p and q is less than r, then the probability of a collision, capital Pi, is 1 minus little r over d, which is reasonably big if r is small. On the other hand, little pi is 1 minus big R over d, which is reasonably small if capital R is reasonably big. Okay. So this is a very simple example of a locality-sensitive hash function. The problem is that these two probabilities are not that good, right? So if half of the bits in there are different, the probability of a collision is a half. So even when the vectors are relatively far apart, the probability of a collision is still pretty big. It's not as big as if the vectors are almost identical, but they're still pretty big. And so I need a way of inflating, I need a way of tearing these probabilities apart. I need to make the probability of a good collision much bigger, and I need to make the probability of a bad collision much smaller. Okay? So the second trick I'm going to do is I'm going to describe sort of a generic method for taking a set of hash functions that are kind of locality sensitive and making them a lot more sensitive. So instead of just picking one hash function, I'm going to pick k times L functions, hij, all from H, independently, where I is between 1 and k, and j is between 1 and L. Okay. Now, I'm going to treat these two indices essentially as I'm going to do an and here, and I'm going to do an or here. Okay, so let me define for any particular for all j, let me define h sub j of p to be the vector I get kj of p. Right, so this is a vector of zeros and ones of length k. Now I'm going to say that this is my hash function. Instead of hashing into a table of size 2, I'm going to hash into a table of size 2 to the k. Okay? But now I'm going to say that 2 points collide if there is an index j such that this vector for p is equal to this vector for q. Okay? So now I'm going to define collide to be for some j, hj of p equals hj of q. Okay. So I'm doing a I'm doing a there exists over all indices j, but in order for these two vectors to be equal, they have to be equal in every coordinate. So you can think of this as for all j, there exists j such that for all I, hij of p equals hij of q. Okay, this is what I'm going to use as my collision event. Okay. Now, what's the probability of actually getting a collision now?
What is hij there?
I'm sorry?
What is hij?
hij is...
Because you only define hi.
No, I defined hij. For all I and all j, I chose a function hij. It returns a single bit.
A single bit.
Right. And then I collected them into these vectors. Okay. So, the probability of getting a collision, what is this going to be? Well, let me first figure out what is the probability of getting a collision hij of p equal hij of q. Let's say if the points are nearby. Then I'm going to get, well, no, sorry. So the probability that there exists something is the same as 1 minus the probability that for all j, I don't get anything. There are, because these are independent, I can phrase this as something to the L. That something to the L, I'm going to get 1 minus, and again, something to the K. And this is the probability that any particular hash function is going to give me a collision. Okay. In terms of the projection onto a single coordinate, this is going to give you 1 minus something involving the distance. That was this. Sorry, there shouldn't be an equal sign here. There shouldn't be a paren there. So you're going to get something like the distance between P and Q over D to the K to the L. All right, so if I've done the math correctly, which I give that about a 50-50 chance, this is going to be the probability of a collision once I've done this weird amplification by building a hash function that actually computes a K by L array of bits and then evaluates collisions using this quantified formula. Now, what does this actually look like? So let me plot out, distance versus the probability of a collision. And the distance is somewhere between 0 and d. The probability of a collision is somewhere between 0 and 1. Okay. Now my original function, this is the probability of a collision if I just use one random bit. Yeah, I'm sorry.
I have 2 questions.
Yeah.
First, the unmatched right parenthesis, where does the K
Yeah, I
lie?
think that's
Sorry, there is a missing. Did I leave out a 1 minus somewhere?
you should open bracket before the first one. The first one you have like.
Yeah, actually, I think this one is the one that's missing. Yes. So probability of a single bit colliding to the K, that's the probability of 2 vectors colliding. And then I want, that didn't happen L times, that's the probability of not getting a collision, 1 minus that. Okay, so let me, as expected, some of the math got screwed up. So start that over. This is 1 minus distance over d, k, the L. Okay. So what's going on here? If I look at a particular bit, a particular function hij, the probability of a collision is 1 when the distance is 0, and it drops down to 0 when the distance is d. Okay. If I just look at, say, this part of this part of this expression, what I'm going to end up with is something that decays not exponentially, but I get this slope that the probability when the distance is 0 is still 1, but it falls off very fast. Okay. This is the probability that hi of p equals hi of q. And the second level of this with the L's, well, first of all, let me stick to this purple thing first. The larger I make k, the steeper this curve drops off. In other words, the bigger I make k, the less likely I am to get a collision when the points are far away. Right. I'm also slightly decreasing the probability of a collision when the points are kind of close but not identical. But you'll see in a second how I adjust for that. The second thing that happens when you put the next layer of wrapper around it is this drop-off actually gets sort of shifted over to the right. So what I end up with now is a probability profile that looks like this. This is the exist J for all I. This is the actual collision probability. And if I set the parameters K and L just right, the little r is going to be on the left side of this hump, and capital R is going to be on the right side of this hump. So the actual values of K and L are going to be chosen exactly the right way so that the probability of a collision when my distance is less than little r is very close to 1. And the probability of a collision when my distance is bigger than capital R is very close to 0. Okay. Now, exactly where this hump is depends on the relationship between K and L. Exactly how sharp this drop is mostly depends on K, but also there's some dependence on L. There's a little bit of a game that one has to play in order to figure out what the right parameters are here, which I don't want to do because it's just sort of math. It's just sort of algebra. But intuitively at this point, you now have an algorithm for doing near neighbor queries with some reasonable confidence. You can say, let me take this matrix of bits and use that as a hash function. The way I'm going to do that is, so let me just write this down. For each point in P, I'm going to store P at, well, there's some table which I'm going to index by HI of P. Okay. And I'm going to do that, sorry, this should be J, for each J. Okay. This is really my data structure. So I've got some table for each one of these vector functions. I have a table that's indexed by that vector of 2 to the k bits. And I'm going to store P in some sort of secondary data structure hanging off of this table. Now, in fact, I don't really want to do this because this table is really big, so I'd actually use another layer of hashing to reduce the space. Okay. And then when I want to do a query, I say, for each j, in query point, I'm given a query point q. For each j, I retrieve everything out of the table at the query point of q. Check every point in S to see if it's close enough. If I find something, if I find a close point, I return it. But one last thing is I stop if it's possible, there's a small probability that this bag in the hash table is going to have lots of points in it, all of which are far away. So there's a failure condition which says stop after checking, say, 2 L points. And then this data structure, or sorry, this query algorithm will find with reasonable probability a point at distance capital R if there is a point at distance little r. There are a couple of failure modes, one of which is all the close points actually didn't collide, but that's not going to happen very often. There's another failure point which is too many far away points did collide, but that's not going to happen very often. Most of the time, some close point is going to collide with Q, and you'll find it. Okay. That is all I want to say about locality-sensitive hashing, which means that is all I want to say about randomized algorithms. I'm happy to answer any questions, but I've already kept you over, so thank you. See you.